Probability density function.
Probability density function (PDF) is a concept used in probability and statistics to describe the likelihood of a continuous random variable taking on specific values or falling within certain ranges. It is like a function that tells us how likely different values of the variable are. Imagine you have a continuous random variable, such as the height of people in a population. The PDF of this variable gives us the probability that a person's height falls within a certain range. However, unlike the probabilities for discrete random variables like rolling a die, the PDF itself doesn't directly give us the probabilities. The PDF graph shows the shape of the distribution and how likely different values are. The x-axis represents the values of the variable example height in centimeters, and the y-axis represents the density of the probability. The PDF graph shows the shape of the distribution and how likely different values are. The x-axis represents the values of the variable example height in centimeters, and the y-axis represents the density of the probability. Remember, the height at a specific point on the graph doesn't directly give us the probability of that exact value. Instead, the probability lies within an infinitesimally small interval around that point. To find the probability of the variable falling within a specific range, we need to calculate the area under the PDF curve within that range. This is done using integration. So, the PDF helps us understand the likelihood of different values for continuous variables, but to get the actual probabilities, we need to perform integrations on the PDF for specific ranges. Making a probability density function PDF can be done in different ways, depending on the data you have and the context of your analysis. Here's a simple and straightforward approach to creating a PDF. Collect data. First, collect a set of data points for the continuous variable you want to create the PDF for. For example, if you are interested in the heights of people, measure and record their heights. Create a histogram. One easy way to start visualizing the data's distribution is by creating a histogram. Divide the range of values into several intervals bins and count the number of data points that fall into each bin. Plot the histogram, where the x-axis represents the variable values, and the y-axis shows the frequency or counts of data points in each bin. Normalize the histogram. To turn the histogram into a PDF, you need to normalize it. Divide each bin's count by the total number of data points and divide the result by the bin width. This normalization ensures that the area under the histogram's bars sums up to 1, as required for a PDF. Smooth the PDF. Depending on the number of data points and the variability in the data, the histogram-based PDF might appear jagged. To make it smoother, you can use techniques like kernel density estimation. This involves placing a smooth curve over the histogram to better represent the underlying distribution. Plot the PDF. Once you've created the smoothed and normalized PDF, plot it on a graph. The x-axis will represent the variable values, and the y-axis will show the probability density. This graph will give you a visual representation of the likelihood of different values occurring. Remember, the PDF provides an estimate of the data's underlying distribution, and it's essential to interpret it in conjunction with the actual data. Also, for larger datasets and more complex analyses, advanced statistical methods like kernel density estimation or fitting parametric distributions may be necessary.
Thank you for watching.